Hi folks, welcome back to Functional Analysis. Now in the two outstanding videos this week, we will discuss one new concept, important concept, several other smaller definitions, prove one theorem, and then discuss a few examples. Okay, so let's get straight to it. Here on top, so we discussed in the very first video actually, we discussed bounded linear transformations, right? So remember we have two normed linear spaces, x and y as written here, and then this notation here means that t is a bounded linear transformation from x to y. So that is a function which is linear and which is bounded. Okay, the boundedness by definition means that there exists a constant c such that for all x, for all vectors in the x space, you have this estimate. Okay, now as it turns out, there can be of course many c's, but all those c's are in some sense upper bounds for t. Now as it turns out, the smallest upper bound that satisfies this inequality in the yellow box, that one plays a very, very important role, and that's why we assign a special name to it. Okay, and this is written here in our first definition of the video today. So given a bounded linear transformation t between two normed linear spaces x and y, again let me remind you, they come with their respective norms that can be different from one to the other space. That's why I indicate this with the subscripts capital X and capital Y. Now what we define is the following thing. Well, it is denoted as t with 4 vertical bars, so we use the norm symbol for it, and this is for a reason. This thing is called a norm, and we will prove in our theorem very soon that this is actually a norm. Okay, but for now, that question aside, whether it is actually a norm, let's study the definition. So you look at this ratio, t of x in norm in y space over the norm of x. Now notice, since t is a bounded linear transformation by the yellow box up there, this is of course a finite quantity, because for any vector x in the non-linear space capital X, this is at most c. So this is finite. Okay, we're not dealing here with infinitely large quantities. Now what we do is, out of all those bounds, as I said earlier, out of all those c's, we're going to select the smallest one. So, and that means we are just looking at the supremum. Okay, so we're going to optimize this yellow bubble here over all non-zero vectors in the vector space. Okay, and then whatever comes out, we denote by this symbol here on the left, and we call it the operator norm. Okay, right now it's not clear that this is actually a norm, but it will be a norm. Okay, so now of course a few comments are in order. So one is, I taught you that norms you can define on vector spaces, right? So the question is, we should first address whether actually this here, so the set of all bounded linear transformation, whether this is a vector space. Well, it is. This is very much like in say calculus. If you learn two functions, then out of those two functions you can create infinitely more, right? So you can add those functions, you can multiply them by scalars, and the same thing you can do with those bounded linear transformations. So if you have, maybe allow me to write this here, if you have two s and t bounded linear transformations, then you can look at those multiples, those linear combinations, alpha s plus beta t, where alpha and beta are scalars in the field. And how do you define this new bounded linear transformation? Well, just as you do it for functions, say on the real line, you define it pointwise, right? So this will be just alpha times s acting on x plus beta t acting on x. Okay, and this immediately gives you a vector space structure. So that set of bounded linear transformations, it is a vector space. So that's why it makes sense to define norms on it. And what we're going to do is, as it is written in the definition here. Okay, so now here's a second equality. So maybe the first one, this is the definition. Now here I write this is equal to this. So the question is, why is this true? Well, this is a property of the norms and of the linearity of t, right? So because if you have this ratio here, what you can do is you can move the denominator. Notice, by the way, the denominator is different from 0 because I optimize over all non-zero x. You can move the denominator inside that norm because the norm is homogeneous, and then because t is linear, you can move it also inside the t, right? So what this ratio really is t of x over norm of x in x space, and then the norm taken in the y space, right? But now as you see, this quantity here inside, x over norm x, that has length 1, okay? That's why you have this equality here, because here you optimize over all vectors of length 1, so on the unit sphere, right? So that's why this is a true equality. And you can go both ways. Right now I explained to you how you can go from here to over there, and well, you could have done the argument in the reverse direction from the right to the left. Okay? Good, so this is the definition. This is what we will call the operator norm. Right now it's not fully clear yet that this is actually a norm, but we will prove this in about 5 minutes. Okay? Good. Now, moving ahead, there will be 2 smaller definitions before we prove that this is really an operator norm. The second definition, now this is actually super important, but several weeks will pass until we encounter what is called here the dual space and the linear functionals. Okay, so let's first study the definition. The dual space of a nonlinear space X is simply all bounded linear transformation from X to the scalar field. That's it. Because the scalar field itself is a vector space. It's a normed linear space because our scalar field is either the real number or the complex number. So the absolute value in case of the real number field or the complex modulus in case of the complex numbers serves as a norm. Okay, so this scalar field is a normed linear space. Okay. And all bounded linear transformations that map into it from X, well, they're very important. They're called continuous linear functionals, and the space itself gets this special notation, shorthand notation X star. Okay, this will play a huge role in chapter 3 of this class. For now, we just have to register this as a definition. I mean, you can anticipate that this plays a role because this class is called functional analysis. So at some point, we should be studying, well, functionals, right? Okay, good. That aside, the last definition for today is something that is already known from linear algebra. This works in any vector space. Here, well, we will only be interested in normed linear spaces, so I just wrote the definition for normed linear spaces. If you have 2 of them, x and y, if you have a bounded linear transformation between those two, there are 2 subspaces. This is the kernel and the range. So the kernel is everything that gets mapped to 0 by the bounded linear transformation t, and the range is everything that gets hit by t in the y space. Okay, this works in any vector space. You don't have to have bounded linear transformation or any of this. However, if you have a bounded linear transformation, then at least one property right now comes to mind. So these are both subspaces, okay? This is proven in linear algebra. If you have 2 elements in the kernel and you look at the linear combination, because T is linear, then that combination will also be in the kernel, and you can do similar things for the range. More importantly, the kernel, this is a closed subspace, okay? This is something you don't discuss in linear algebra. So let me quickly fill in the details. So how do you show that a set is closed? Well, you take a sequence in the set, assume it is convergent, okay? And then you have to show that the limit is also in that space. Yeah, but this works because we're working here with bounded linear transformations, and those guys are continuous. This was our very first theorem in this class, right? Because now what you do is you look at Txn, Now, since t is bounded linear, continuity lifts that image sequence to a convergence sequence, so you have this. Yeah, but since xn is in the kernel, all these images are equal to 0, right? So that's why as n goes to infinity, also this limit here has to be equal to 0, and that means in turn that x is in the kernel of t. In short, kernel of t is a closed subspace. Okay? This is not true for the range in general. Not closed in general. Okay, we will encounter this in the exercises. There will be an example where you will have to prove that, well, for this t on that and that space, the range is actually not closed. Okay, good. Very nice. So we have these three definitions. We have the operator norm up here. This is right now the most important one. We have the dual space and continuous linear functionals. This is for later use. It will be very important. And kernel and range, those two subspaces, kernel being a closed one, range not necessarily. We will encounter them frequently throughout. That's why I thought I put the definition here up front. Okay, now we will now prove that, well, the operator norm as defined earlier is actually a norm on the vector space of bounded linear transformations. Remember, this is a vector space. I gave the argument earlier how you define the operations in there, and we will show that this as a normed linear space, right? Because if I prove that Lxy is a normed linear space, I can talk about completeness, I can talk about Cauchy sequences, whether they have a limit. And we will show they actually are all convergent, provided, well, the target space Y is complete. Okay, this will be our goal. All right, so let's get started on that. So first, we will address whether this is an operator norm, or whether the operator norm is a norm. Okay, so recall, how was it defined? For T, L, X, Y, we defined norm of T as supremum over all non-zero vectors, and then the ratio of these two norms, Tx over x. Again, this is well defined because T is bounded linear, I showed you earlier. So now, is this a norm? Well, I have to check three properties. I have to check whether it is positive definite, whether it is homogeneous, and the triangle inequality. Okay, so for positive definite, well, if this here on the left, let's do it here, positive definite. For this, I have to let the left-hand side be equal to 0 and then conclude that this can only happen if T is actually the 0 transformation. Yeah, but look, if you have this here equal to 0, now you're taking here a ratio of two non-positive, or not, the denominator is always non-zero, the numerator can be 0, of course. So how can this ratio only be 0? Well, it can only be 0 if the numerator is equal to 0, right? And since you're taking here a supremum over all vectors, this means in turn the numerator has to be 0 for all vectors small x in the normed linear space capital X. Yeah, but by the norm properties then of y, this means that T of x has to be equal to 0 for all x in X. Yeah, but this is precisely saying that T is the 0 operator. Okay, so T is equal to the 0 in Lxy. So careful here, there's many zeros floating around. This 0 up here, this is the 0 vector in Y space, whereas this one here, this is the 0 linear transformation. That's why I wrote it here. Okay, so positive definiteness is clear. The homogeneity doesn't, as usual, doesn't need any further comment. Homogeneity, because if you have a scalar in there, then the scalar will appear up here in that yellow bubble. Yeah, but that yellow bubble itself is a norm, so it's homogeneous. You can pull out the scalar, and then the scalar sits here, and then you just pull it out of the supremum. Okay, so there's nothing to be shown here. Well, the lambda comes out, of course, in a complex modulus, so you will have lambda t. Okay, so this is true. Now the only thing that requires, as usual, some work is the triangle inequality. So let's do this. The trick is always, whenever you see those suprema, first don't take them into account, just work with arbitrary vectors, and then at the end, once you have your inequalities, you optimize. So we will do the same thing. Okay. So for any x in x, let's look at s plus t x. Now, okay, so these are in y space, so by the definition of that sum, this is x of s plus t of x, y. Then you use the triangle inequality in y space, so you get s of x, y plus t of x, y. And now you optimize individually the left-hand sides, okay? Let me move this a little bit here to the left to have more space, okay? So this is true for all x in the vector space. So in particular, when x has a length 1, this is certainly less than or equal than the supremum over all those vectors of length 1, sx, y, plus you optimize individually, sxy, txy. Yeah, but these two quantities, the first one is precisely the operator norm of s, the second one is precisely the operator norm of t. So what you have shown is that for all vectors x on the unit sphere, that quantity on the left is at most the sum of those two quantities on the right. Since this holds for all x on the unit sphere, you can optimize, and that will give you that s plus t, which is the supremum over those vectors of length 1 of s plus t x. Let me erase this. S plus tx in y is at most s plus t, right? And this is the desired triangle inequality. Okay, so this thing indeed is a norm. Okay, good. So now first part is done. Now the second part, we have to show something about, well, Cauchy sequences being convergent, aka the completeness. Okay, so next. So let Tn, so this is a sequence of linear transformations, be a Cauchy sequence. Okay, so now I have to show that this thing has a limit, which itself then is a bounded linear transformation. Okay, then for any x in x, let's estimate a little bit. So Tnx minus Tm of x in y space. Now, so this is Tn minus Tm x in y space. And now here comes a useful trick. So that's a trick to remember. How can you optimize this guy? Well, suppose x is different from 0. Actually, this will be inequality. I'm not estimating yet. Then what I do is I write this, well, artificially like this. So I divide by x and I multiply by x. Okay, so now that first ratio here, that you optimize. So you go supremum x, x in 0, and then the same ratio, Tn minus Tm x, y, x, x, and the supremum stops here because the other guy you don't touch. So you have this. Okay, but what you have now here in the closed brackets, well, that's exactly the operator norm of the difference, right? So you have this. Okay, yeah, but Tn was a Cauchy sequence, so it's convergent in the operator norm, right? So what this shows, so this sequence Tnx from 1 infinity in y is Cauchy for all x in x. Okay, now careful here. Apparently this inequality up here used the assumption that x is non-zero. Now down here I say this is true for all vectors in the vector space. But you see, if x is the zero vector from the get-go, then both sides here are equal to 0. So inequality is still true, right? So this is certainly a true statement that is Cauchy for all x in x. Okay, good. Now since y is complete, it is therefore convergent with limit, let's just call it y in y. And this quantity y, of course, it depends on the x that you insert there in the sequence Tn of x. Okay, now what you do is now define map T from x to y via, well, T of x is precisely equal to that quantity y, which depends on x, right? You can indicate it like this. Okay, now I have to check a few things. This map is linear since, since for any two vectors x1, x2 in the space and scalars alpha, beta, we have, okay, so we were gonna look at alpha tx1 plus beta tx2, and hopefully by the end of the day I will obtain that this is t of alpha x1 plus beta x2, right? So now hopefully I will achieve equality here, because if I do, then this says precisely that t is linear. So how to do it? Yeah, well, you have to remember, so t of x, this is a limit, right? So we have that this is equal to limit as n goes to infinity alpha tn x1, okay, plus beta tn x2. Okay, yeah, but the Tn's, those were bounded linear transformations. Tn was a Cauchy sequence in the space of bounded linear transformations. So here I can now use the linearity t of Tn. So this is limit n to infinity, and then Tn alpha x1 plus beta x2. Okay, yeah, and that's it. Because that limit, by definition of t up there, is precisely equal to this. Okay? So that shows that t is linear. Okay? This map is linear. Okay? Also, we have to show that it's bounded. Also, t is bounded. How do we do that? Well, I have to estimate t of x in the y norm. Yeah, but here is the argument. So t of x, which we called y, is the limit of Tn of x, sort of the limit here in y. But now remember, I think in the second lecture, we used this triangle inequality, the lower end triangle inequality for the norm. Okay, so that one says that the norm as a function from the vector space to the non-negative real numbers is Lipschitz continuous, right? So that allows me now to pull out that limit because of continuity, right? So limit n to infinity tnxy, okay? And now I'm going to use the same trick that I did earlier, okay? So I'm not going to touch the limit. I'm going to estimate this again as tnx over x, and then multiplied by x, and the first ratio I estimate by the operator norm. So this is tn times x in x space, right? So here to keep track, these are in x, these are in y. So I have this. Yeah, but each tn here was a bounded linear transformation, so there exists constant c, then you can estimate this, you can take the limit, so you will still have that this is less than or equals Cx for all x in the vector space. Okay? Little bit of thought here has to now argue why this constant cannot depend on small n, right? Because each Tn is a bounded linear transformation. So for each Tn you could think there exists a constant c which depends on n. So how can I guarantee that this actually does not explode as n goes to infinity? Well, the reason is, let me write this here. So Tn, this sequence, is Cauchy in R. Okay, this is a Cauchy sequence of real numbers, and every Cauchy sequence is bounded. That's why here this constant actually is n independent. Okay, and that's why you have the result. Okay, but that is it. Also T is bounded, and this completes the proof of the theorem. The proof of the theorem. In the exercises, we will see that in general, once you drop the requirement that y is complete, the non-linear space of bounded linear transformations from x to y is not complete. We will see this in the exercises. So that requirement is essential. Okay, I will stop here. See you in the next video.